Hello, my name is Mikkel Brødegaard, and I will explain here the hyperspectral elastic LIDAR, which is based on Supercontinuum light sources and indium gallium arsenide camera. Okay, so this is a Scheinflug LIDAR. This telescope here is a Newton telescope. The focal length is 800 millimeter and the diameter is 200 millimeters. So the primary mirror is down here, and the secondary mirror, which is flat, is then folding the light up here to the image plane, which is then tilted. And inside here you can see we have a tilted slit here, which then satisfy the Scheinflug condition. Okay, so this unit here, which is 3D printed by Lauro Müller, this we call the spectral analyzer. So it takes the light and disperses it perpendicular to the slit and projects it on the indium gallium arsenide camera, which is up here. Okay, this here, it controls the focus of the of the receiver, and it has a lock here. It has a focus engage here, and it has a focus lock here. So you can tighten the focus lock here, and then it will block the focus of the receiver. And this one has to be engaged for me to control this, and this one has to be opened to move the focal focus stage. If you are out of focus with the receiver, and if this receiver is a Newton telescope like this one, your echo will be bimodal. It will not just blur out, it will get a hole in the middle, and the reason for that hole is a secondary mirror. Okay, so it's possible to distinguish between defocusing of the receiver and defocusing of the transmitter because of this mirror here. So if you see a bimodal focus echo in your signal, it's because the receiver is out of focus. Okay, and this focus can then be adjusted here. Another thing is that the line here has to have the right rotation, so we might need to rotate this to get the image of the illuminated air volume to align with the slit here. Okay, the easiest way to do that is if you have an air signal or a signal from some fog or something like this, then you optimize it to get the maximum signal in the middle of your slit or in the middle of your sensor. And that you do with the overlap. I will come back to that up here. And then you rotate it here to get your echo distributed across your whole sensor. Okay, so that was the receiver part here. Up here we have the beam expander. The Supercontinuum is here. It has a fiber collimator, so it comes out as a pencil beam here. Right here we have a negative lens which diverges the beam. It hits here a dichroic beam splitter, and we throw out the visible part. Only get the infrared part here, and we have an infrared filter here where we split everything below 850 nanometers. And then we transmit it here with the tap here. We use this focal stage to control the divergence. So this we call focus, and this we call divergence here. Okay, now the transmitter here is placed on a tangential mount. This is this one. Tangential means it can point in different directions. and it doesn't have any springs, so there are 2 screws here and they counteract each other, so you have to rotate them simultaneously in the same direction. Then you can change this angle here. This angle that we have here, we call it slant angle. This position, it controls which pixel on your camera corresponds to infinity. Right, that's the slant angle. And when you want to lock these, you turn them in the opposite direction so they press in like this. There are 2 more controls up here. These are called the overlap function. And this will turn the beam perpendicular to the baseline like this. And it will put your image of your laser beam on top of your slit. So there are multiple degrees of freedom to optimize. We want to collimate the beam, that's divergence. We want to have it in focus here with the receiver, that's a focus. We want to have the right rotation, and we want to have the right overlap angle. Another small detail, if you change the slant angle, you're changing your range calibration, and so you change what pixel corresponds to what range. Also, because the sensor and the slit is tilted, you're also changing focus at the same time. So if you change the slant angle, you need to refocus. The most sensitive part is normally the overlap. And it is a very tiny adjustment to optimize it. Another word of wisdom is that, for example, if you have a long range here and a termination point far away, it's not enough only to optimize the strength of your termination point. You have your slit here and your laser image of your illuminated air volume here. So the overlap controlled like this. You also need rotation like this, and you need focus on the same line. So if you only optimize for the far point, it's possible that you're not overlapping for the rest of your sensor. Okay, so you need to also have the right rotation. Okay, another typical thing is that it's possible that you get the rotation right, and then when you then do the focus, then it's possible that your signal diminishes, because when you get the right focus, it might focus next to your slit, right? And then you have to move it in and do the overlap. So you have to go through these parameters until you reach the optimum in this alignment procedure. And sometimes if you improve focus, your signal can deteriorate because it's not in the right overlap or the right rotation.